It's great pleasure to have Professor Semeon Arthamonov, who is going to talk about quantum modular spaces of flat connections bridging different areas of mathematics.
Good evening, and thank you very much. So it's a big honor for me to become member of BIMSA and being invited to a member seminar. And in my talk, I'm going to show how the study of the quantum moduli spaces of flat connections brings together so many different areas of modern mathematics. It is very successful at doing so precisely because it is deeply rooted in the laws of nature. Sorry. Working. So in 1954, Channing Yang and Robert Mills proposed a theory which is now known as non-abelian gauge theory, or simply Yang-Mills theory. So this is the theory which today describes the theory of electromagnetic, nuclear weak, and nuclear strong interactions in a uniform manner. Behind this theory was one key brilliant idea, that the particle fields of an elementary vector bosons correspond to a Lie group valued parallel transport function. So what is a Lie group valued parallel transport function? So to every smooth path gamma from the point P1 to the point P2, it assigns an element of a Lie group in a uniform manner. So it's smooth and nice, but what's most important is that it behaves well with respect to the composition of paths. So for a composition of paths, it will assign the product of the two group elements. For the path walked backwards, it will assign the inverse group element. So the idea of Yang and the idea of Yang-Mills theory placed already by that time well-established areas of general mathematics, such as the theory of Lie groups and differential geometry, right at the core of the high-energy physics, where it remained ever since. Now, of course, you cannot measure particle fields directly on the experiment. In fact, one of the postulates of the gauge theory explicitly prohibits you from doing so. So what you can measure? You can measure something that is invariant with respect to the so-called gauge group. And in 1974, Kenneth Wilson formalized what was already in the air by that time, that the fundamental class of observables are the so-called Wilson loop averages. So those are the averages of the class functions associated to a closed loops, some invariant G-invariant functions associated to the closed loops. Okay, so another step in the development in the relevance of the moduli spaces of connections happened in 1989. When Edward Witten proposed to consider a special type of the Yang-Mills theory with the Chern-Simons potential, for which the corresponding parallel transport function doesn't change as we smoothly deform one path gamma 1 to another, relative to the endpoints, of course. So this got a name of Chern-Simons theory. And what he has shown that the fundamental observables in Chern-Simons theory are nothing but just appeared Jones polynomials of knots, which are now topological invariant because they do not depend, they do not change with the continuous deformation of the path. Okay, so the mathematical framework of the Chern-Simons topological theory was then developed by Retakh and Turaev. So in this theory, you can exactly compute all the observables, and the modern mathematical formulation was given by these authors. So the ideas of Witten, Retakh, and Turaev placed the moduli spaces of flat connections right at the crossroads of modern mathematics. So they have been already by that time related, of course, to mathematical physics, Lie groups and algebras, in differential geometry. But the appearance of the topological quantum field theory, the Chern-Simons theory, brought them in a close relation with representation geometry, representation theory, and topology. Okay, so let's talk about the most basic case of the flat connections of the. Oh, that's a good question. So I promise that at least the action of SL2Z will appear today. It will not go as far as I would want it to, because this one is the hardest one. So that's a good point. But there is one. Okay. So yes.
That's in the level of partition functions induced by this.
And characters.
Is that yeah? Okay.
Yeah. Anyway, so that will be beyond what I will really be talking today. But thanks for pointing this out. Okay, so let's move on and let's talk about the example of a moduli space of flat connections, which would be the simplest you can ever imagine. Well, I mean, you cannot do anything interesting in the one dimension, right? So let's talk about the moduli spaces of flat connections of surfaces. Now, our parallel transport, as we just agreed, it would not change with the continuous deformations of the paths relative to the endpoints. So the only values of the parallel transport function we would care about are on equivalence classes of paths, modular continuous deformations. So this set of equivalence classes is well known for a surface, and it is called fundamental group of a surface. So in the case of a torus, this fundamental group would have two generators, namely the latitude and the meridian of the torus. But these generators will not be independent, right? As there are paths which can be continuously shrank to a point. So in the case of the torus, that would be the group commutator of the paths along the along these two cycles x and y. Okay, well, that was a very simple example. In general, of course, fundamental groups are non-abelian, but for closed surfaces, they would have a very simple presentation in terms of generators and relations. So this is, for example, what you would get for the closed surface of genus G. And you can get it for non-oriented surfaces. You can get it for surfaces with boundary, and so on, in the same manner. Okay, but we're interested in the parallel transport function, right? So we want to assign some elements of a Lie group to our paths. So let's follow the logic and let's take the most basic example of a Lie group we can possibly imagine, and that would be SL2C. So let's look. So any homomorphism from the fundamental group of a surface to the group of a 2x2 matrices with a unit determinant is defined by its image on the generators, right? So the two matrices x and y in SL2C of determinant 1. Now, of course, those matrices better be satisfying the relations in the fundamental group. So those can be written as an algebraic equations on the elements of a matrix. And if we look at all possible matrix representations of the fundamental group, they would form the so-called representation variety, which basically is the variety cut out by the polynomial equations that the determinant of x equals to 1, determinant of y equals to 1, and that they satisfy the relation. Now, on this variety, we will have the action of the underlying Lie group, right? So GL2C would act by conjugation. So you can ask, what are the invariant functions? So those will be the fundamental observables. Those will be the one which are invariant under the action of the gauge group. So in the coordinate ring of this representation variety, you can select the invariant polynomials. Well, in our basic example, the entire ring of invariant polynomials would be generated just by 3 elements. So this is the trace of x, trace of y, and trace of xy, subject to one single relation: a squared plus b squared plus c squared minus abc minus 4 equals to 0. Sounds okay, great question. The action of the GL, of course, would by conjugation would factor through the action of the SL. So okay, so now looks simple in this very basic example, but here I have to make a remark that the character varieties get very complicated very fast, to the extent that one day you might come up with a collection of generators and relations for some simple character variety in SL2C, and kind of that would be the last lemma which you need to prove in the paper before posting to archives. So you look, who do I cite before I upload it? And then like, oh no, no. And you spend 2 years proving that this is actually the complete set of relations. So, okay. Anyway, so totally unrelated to my experience. So, oh, sorry. So I put the variety here in quotes because what is easy is to select the ring of invariance. Well, normally this ring of invariance does not correspond to the coordinate ring of a variety. So, or at the very least, it will be singular, like in this example. Okay, so let's go ahead and plot the real slice of the variety of the genus 1 character variety SL2C. So the implicit function theorem from the multivariable calculus tell us that the singular points of this variety are precisely where the gradient of our single relation vanishes. Well, there are exactly 4 points where the gradient of this function would vanish, which would correspond to the singularity of our variety. Now, in algebraic geometry, there is a standard way of getting rid of singularities called the blowup. So, and in this particular example, we have only isolated singularities. So this is fairly easy to explain. Let's just look, unfortunately, animation already started. Let's just look at the singular point. So in the vicinity of our singular point, our variety looks like a cone. Well, this is just a picture of a real slice, so don't get too excited. So the blowup, in simple terms, corresponds to the following operation. We just take our singular point, and replace it with a set of directions we can approach the singular point. Of course, behind that there is an actual algebraic equations which do precisely that. That's called the blowup, which in this particular example would literally do what's written in this picture. So this is a fairly standard procedure, and the large class of singular varieties can be made free of singularities by finitely applying this blowup. But we want more. We want more because our character variety wasn't just the coordinate ring of our character variety wasn't just the ring. It was equipped with an additional structure, which I kind of hide it under the rug until now. And the truth is that there is a symplectic structure on the moduli spaces of flat connections of a closed surface. So this was induced by the Atia-Bott symplectic structure on all flat connections. And in a finite dimensional case, it was first described by William Goldman. So today it is called as Atia-Bott-Goldman Poisson bracket. So in this case, I won't tell you what the Poisson bracket is, except that this is an operation to which you feed two functions, it gives you another. And it will satisfy Leibniz identity in the both arguments. So it's enough to write it on the generators. This is it. So the beauty of this resolution is that not only it gets rid of the singularity, but what you get in the end is also a symplectic variety. So the blow up is a fairly general procedure. You can start with a singular. You can start with a singular variety, and you can just do enough blow ups to get to something smooth. But if you start with a variety which has symplectic structure on the smooth part, it is a very rare property for the resulting variety to be symplectic. This one is. In fact, kind of this one is. There is some reason for that, to which I will come back in 2 slides. But for now, let's go ahead and talk about the quantization. So, kind of those of us who attended the quantum mechanics course would pretty much kind of start the semester by a very simple mantra that you take the Poisson bracket and replace by a commutator, and magically everything works. We know better these days, thanks in particular to this gentleman. So for mathematicians, the quantization of a Poisson algebra really means a family of associative algebra, which are labeled by one parameter, h bar, Planck constant. So, and the idea is that all these algebras for all values of the parameter have the same underlying vector space. It's just the multiplication operation that we deform. When h bar equals to 0, that's the commutative algebra. And that's the coordinate ring of our original variety. Or for physics-minded people, that would be the coordinate ring of the phase space. Now, in mathematics, you don't think about the spaces, you think about the rings associated to the spaces, right? So kind of you can nicely deform the ring, get non-commutative coordinate ring of the quantum moduli space. So this is what this A and H bar stands. And the non-commutativity will be controlled by this Poisson bracket. This means that as H approaches to 0, your algebra is almost commutative, and the first correction is your Poisson bracket. Okay, so the reason that our resolution of singularities for the genus 1 SL2 character variety resulted in the symplectic variety is precisely because there is a meaning of the both quantized and deformed modular space. So the double affine Hecke algebra came from completely other branch of mathematics, namely algebraic combinatorics. So in 1995, Retakh used the double affine Hecke algebra to solve long-standing Macdonald constant term conjecture. So the first application of this algebra had nothing to do with the moduli spaces, geometry, and so on. But the key why this worked was that this algebra admitted a very large group of automorphisms, which had topological origin. So this SL2Z is nothing but the modular group of a torus. So it then appeared that in later papers, much later than the original work of Retakh, that this is really a flat family of algebras which both smoothly deform the genus 1 character variety and quantize it. So there are two parameters, the deformation parameter and the quantization parameter. So that deformation parameter is precisely what have been varying on the animation with the resolution of the singularity. So that's precisely kind of the one extra parameter you can introduce in your variety. Okay, and those of course exist for all root systems, and that's kind of this is in fact not the entire double-affine Hecke algebra, but this is just a spherical subalgebra of that. But we're not going into such details. Okay, and these algebras exist by kind of by a fundamental reason. Okay, so I started my presentation by saying something about the Lie groups, right? So I have to return to the subject. So like I already said, symplectic resolutions are rare. And in fact, they are so rare that people kind of actively searching for new examples with which you can work with explicitly. So this led Bellamy and Shedler in 2019. Well, in 2019 that was published. It was probably a few years before that, to actually classify all character varieties which admit symplectic resolution. So what they've shown is they all symplectic singularities. That's unsurprising part. But they admit symplectic resolution only in two cases. So the genus equals to one case. That's a well-known example. And the one special case when the genus equals to 2 and the group is SL2. All others do not admit symplectic resolutions. If you do a blow up on the varieties, you won't end up with a symplectic variety. Okay. So this example was well known, and the quantum version of that is related to the double-affine Hecke algebra. So basically, the double-affine Hecke algebra and this whole story exists precisely because the genus 1 character variety admits symplectic resolution. Yes? So this one will be 6. The most relevant. The most interesting to me would be 6. Of course, the smooth locus. So symplectic resolutions are rare, and major examples of symplectic resolutions come from the nilpotent cone of Lie algebras. Another, but closely related, is this double-affine Hecke algebra. So this led kind of some other brilliant people, including Andrei Okounkov, to propose what's kind of to propose a philosophy which roughly is called symplectic representation theory. That kind of one might expect that the methods of the usual representation theory of Lie algebras can be translated to general symplectic resolutions. The main obstacles is that there's not so many good examples which are as explicit as the nilpotent cone of the Lie algebra. So kind of now we know that the genus 1 symplectic resolutions correspond to the double-affine Hecke algebra. Well, this should be a wiggly line, a lot of skipped here on the way. So there is this mysterious resolution. Should there be a genus 2 double-affine Hecke algebra? Yes? Don't know. That's the great question. Wouldn't pretend that I know the answer. So
maybe
yes.
Another thing that could clarify. So quantization and deformation you can do any algebra.
Oh, sorry.
So what is needed to make sure that it's a double
Excellent,
affine Hecke?
excellent question. So it's not just the deformation, it's the flat deformation. It's the deformation which gives you the family of algebras which share the same underlying monomial basis, and those can be classified by homological means. And at least for symplectic resolutions of conic singularities, this one is not, because there are several points. There is no C star action or anything like. There's a theorem that existence of symplectic resolutions implies the existence of a flat Poisson deformation of the underlying coordinate ring. Of course, we believe that it works beyond toric singularities, which is this one.
Flatness.
It's the flatness condition that is the key here. Okay, so thank you very much for introducing my next slide. So in 2019, absolutely not thinking about symplectic resolutions or anything like this, me and Semeon Arthamonov proposed an algebra which kind of generalizes the double affine Hecke algebra, well, spherical subalgebra of the double affine Hecke algebra for the genus 2. So we propose it as an algebra of difference operators. So roughly, these are commuting Hamiltonians. These are multiplication operators. So there is a common system of eigenfunctions for these commuting Hamiltonians, which we solved. And kind of what was built into our construction is that the mapping class group of a genus 2 surface now acts by automorphisms of this algebra. So this algebra has huge collection of automorphisms, which is the mapping class group of a genus 2 surface. Well, at the time, we could not, of course, kind of our goal was to deform the skein algebra of a genus 2 surface, but we could not prove that. So in 2021, Juliet Cook and Peter Samuelson came up with a theorem that indeed for generic Q, our algebra of difference operators is isomorphic to the quantized character variety known as the skein algebra. Well, but it still didn't give us the monomial basis, or in fact, we didn't have the presentation in terms of generalities and relations. So it took a while to prove that this is actually a flat family. And that kind of to find the monomial basis, solve the work problem, and show that this specialization is indeed the character variety of the genus 2 surface. So thank you very much for your attention.
All right, fantastic talk. Questions?
Thanks. So the question about genus 2. So the part of the reason why genus 1 works so well is because the modular space is not just symplectic, but it's holomorphic symplectic, right? So you can have you can rotate, you can choose the complex structure, and then so in fact, I mean, you probably didn't want to talk about it, but the way quantization works, you have like there's the quantization parameter h bar is a complex variable, right? And as you change it, there's a certain flat family which you can go along, and then it looks different in different complex structures, right? So in genus 2, is it also homomorphic symplectic, or?
So in our construction, everything is by default over the field of rational functions over Q and T. So is that what you're asking?
Homomorphic symplectic means you double everything. So say for genus 2, you have dimension 2, but now it becomes quaternionic dimension 2. So you double all the degrees of freedom.
Cannot answer immediately, but would be happy to discuss it with.
So we have this paper with Gukov and Nawata and others, so where it's kind of we do what is called quantization by branes, right? And where it's important that the modular space is homomorphic symplectic.
No, Peter, but we didn't look into this. So
okay, yeah.
Thank you.
More questions?
You told us that the Hecke algebra is related to McDonald conjecture. What is the combinatorial content of your own algebra?
That's a great question. We did not investigate that. So we can compute what we call genus 2 McDonald polynomials using the Pierre rule, show that they are common eigenfunctions to this system of quantum operators, quantum Hamiltonian operators. They contain the SL2 McDonald polynomials as particular case. So you expect that there should be some meaning of the constant term. I don't know this, so but that's an absolutely great question.
Okay, thank you.
What about generalization to other groups, supergroups, other series?
That's also an awesome question. So
is something known, maybe just potentially?
So now if we go here, then this is the, if we talk about just the usual character varieties, then this is it. So at first we were even disappointed that this is a very special example before we came to this paper and realized why this is special. But if you look at the finite quotients of character varieties, there are examples like that, which would also admit deformations. Now for the supergroups, I didn't think about this, but this is another great example. I don't know the answer. Great question. I don't know the answer for more general cases. But certainly in the naive character varieties, this is an exhaustive list.
Yeah, but usually if you have something for GLN, you have almost always non-trivial generalization to super GLN. Okay, very rare. Very frequent.
So,
yes.
Did I correctly understand that your algebra is analog of spherical Dachau? Yes.
Yes, that's right.
And
we don't know how
non-spherical
version.
Full Dachau?
We don't know we of course thought about this question and we wanted to get the full Dachau. We cannot we could not come up with a construction, but that's excellent. That's an excellent question.
Okay, thank you.
You have mentioned that there's a relation between this algebra and the scaling algebra, right?
Yes, it's just let me go back to a beautiful theorem by Juliet Cook and Samuelson. So particular case of this algebra, when Q equals to T, when you set the two parameters equal to each other, is just the skein algebra of a genus 2 surface.
Okay.
So this gives you a presentation of the skein algebra of the genus 2 surface in terms of Q difference operators.
Mm-hmm. So actually, I have two questions. So is this picture generalizes to higher genus? Is there a problem?
There won't be T. That's the. So naively, there won't be. So it's a theorem that there won't be flat deformation of the skein algebra for higher genera. But of course, like with every no-go theorems, you slightly change your assumptions. So if you talk about closely related by different problems, there might be meaningful things to do there.
I see. I ask because the scaling algebra is always there, right?
Skein algebra is always there, but this extra parameter you can only add in the genus 1, and you can add it in the genus 2 and SL2.
I see. And another question is that what about the root of unity? You have mentioned that this is true for.
You covered precisely kind of everything I had to exclude from my presentation. Thank you. So in the at the roots of unity, skein algebra admits finite dimensional presentation. All right. So and this is actually how we came up with this algebra in the first place. We were studying the deformation of projective representations of the genus 2 mapping class group. So we first came up with the finite dimensional representations of this algebra, which happen not at the roots of, not when the Q roots of unity, but when Q to the K T squared equals to 1. This is the same identity as in the Dachau. So then this algebra admits finite dimensional presentation, and you can write it. You can find the basis there. You can find the matrices and so on. Yes.
Thank you.
Thank you.
Okay, question at the front.
Yeah, maybe one more general question. So what is the consequence of this algebra for Chern-Simons theory, since you mentioned it at the beginning?
So that's the kind of, thank you very much for that question. So we started this product with Shamil by trying to generalize their results with Semeon Arthamonov in the genus 1 case. So the algebra of operators of the Chern-Simons theory in the genus 1 case admits one parameter deformation. And this is kind of roughly corresponds to the deformation. I mean, that's the same extra parameter t, right? And this algebra would realize finite dimensional presentations of the Cherednik algebra. So that was. No, this means that this is an algebra. So TQ of t assigns an algebra to every closed surface, assigns an algebra. So for Chern-Simons TQ of t and genus 1 surface, this algebra would be a finite dimensional representation of the skein algebra at level k. So our original idea is, this Aganadic and Shakirov theory in genus 1 can be used to calculate the super polynomials of torus knots, which are related to the Hovanov homology. So our original idea was, okay, so how about we come up with a TQ of t, which calculates the Hovanov homology. So these are knot invariants, which are notoriously hard to calculate, right, compared to the Jones polynomial. We were both graduate students at the time. So every smart person around us told us that that's not going to work, rightfully so. But we did it anyway. So, what we came up with, the finite dimensional representations for this algebra. Then, of course, it didn't generalize beyond this case. We were disappointed, but kind of not as ambitious. Won't give us much mileage, but still a lot of interesting algebraic questions. So we did the representations in, I think, 2015, and then couple years we were writing the paper to find the algebra behind these representations and so on. And then we realized that that this particular construction is not uninteresting because it's special. It is interesting because it's special. So getting more general Chern-Simons theory was our original motivation. Doesn't work exactly as we wanted. Now we know the reasons. Whether you can make it work by looking at something we didn't notice, I don't know. So, but thank you for the question.
Yeah, maybe Semeon,
Yes.
one quick precision. That's along the lines what Babak was asking. Now, have you thought about this realization of this of your algebra as Daha, and which would play a role for this triality when people think of quantization that Chern-Simons, looking into the gauge theory like Rutgers, Douglas reduction, and then something what people call double scaling SYK, because for all of this, the skein algebra is a unifying algebra, quantum. Q-deformed, I have to be precise, Q-deformed skein algebra. Maybe it's a proper way to think, but it's still incomplete in this triality. Maybe it's, have you thought?
Never came to my mind. I would be happy to talk about it.
Yeah,
So,
because maybe it's a proper way to think about this in terms of Daha and not.
So maybe a naive question. This theorem that you said, if you have the symplectic resolution, it induces a Daha. So can you go back?
This is not a theorem. This is a chain. This is a chain of theorems, and actually, there are some details which are carefully excluded from that. So the theorem is that if you have a resolution of the conic singularity, then the underlying Poisson algebra admits a flat deformation. Strictly speaking, it doesn't apply here. But actually, if someone knows how to find in the literature a theorem which would apply, I would be very happy to hear about it. But of course, everyone expects this to work here, and that would be exactly that flat deformation. So that's an excellent question. I deliberately hide it under the rug.
Another question, which is naive, is can you go from right to left?
Oh yes, In fact, of course, with Shamil, we came up with the
so
quantum. So you can recover. So this is you cannot recover the resolution, but you can recover the flat Poisson deformation because that's the classical limit of this system. So if we go here, then it takes exactly. The year doesn't appear here, so it should be 2023. So it takes exactly 4 years to go from the quantum to the classical case, because this involves solving the word problem, finding monomial basis. But yes, you can to a certain extent.
Okay, fantastic. This is a great talk. You see, short talk and intrigued all of you to ask questions. Beautiful presentation. How did you do your slides? Those animations, how did you do
that's in Mathematica.
That's Mathematics.
Yeah.
That's do this one.
That's the Miro online Blackboard. You can in fact open the link on your smartphone and scroll my slides independently. I normally do it in the talks, but not on the member seminar talk, because I didn't want people to see what was going next.
So do you have a conjecture about categorical statement?
Oh,
like representation category versus Fukaya, that kind of
thing. That brings us there is a well formulated collection of conjectures about the positive basis for the Aĥine algebra. We don't even know it here, So how to prove it? In principle, you can do something in the TD form case as well, but that's completely unexplored by me, I would say. So this, Peter, we should bring it to the coffee room.
All right, more basic questions. Why genus 2?
Genus 2 is 1 plus 2. That's the you basically go down to the tangent space at the trivial representation. You analyze there a lot of work. So this is this looks simple, but this paper what? So I cannot summarize this paper in a few words, because I have to understand all the details of the proof. So, but basically you boil everything down to the statement in the vicinity of the trivial representation. So.
Okay, let's thank Semeon again.